We have come a long way from pure simulations in mill and sill to testing real processors in pill and full ECUs in hill. Now we introduce something truly human, the driver. Welcome to the world of driver in the loop DiL, the stage where the human element joins the test loop. While mill, sill, pill, and hill focus on machines, DiL brings the driver to see how the person behind the wheel interacts with all that technology. So, what exactly is DiL? In simple terms, driver in the loop is a test setup where real human driver interacts with a driving simulator, a virtual environment that combines realistic vehicle dynamics, visuals, and feedback systems, all connected to the same control software and ECUs you have been testing through the earlier stages. This stage bridges the gap between lab based hardware test and real world road test. It's about answering one key question: how does the human driver perceive, react to, and influence the vehicle's control systems? Because at end of the day, no matter how advanced your algorithm are, whether it is for steering assist, braking, or autonomous driving, they all must feel natural, intuitive, and safe to the human sitting behind the wheel. Let's break down how this setup works. Imagine a driver sitting inside a motion based simulator cockpit, complete with a steering wheel, pedals, dashboard, and screens that project a 360-degree view of a virtual environment. Now, inside that simulator, the vehicle model plant runs in real time, simulating vehicle dynamics, tire models, and environment physics. The ECUs or control software are connected, either real hardware from hill setups or their virtual counterparts. The driver interacts naturally, accelerating, braking, steering, interacting to visuals and forces. The entire system operates in a closed loop. The driver provides inputs, the vehicle model and ECU respond, and those reactions are fed back to the driver through visual, motion, and haptic feedback. This forms a real time human machine system. It's like a video game but with the full engineering precision and real automotive control logic running underneath. So why is DIL so important? Because when your ECU works perfectly in a lab, it might not feel right to a human driver. For example, suppose your electric power steering system works flawlessly in hill, but when a driver uses it, they feel the steering is too light at high speeds or too stiff at low speeds. That's a human perception issue, something you will never catch with hardware or code alone. DIL testing helps engineers evaluate exactly that, how humans perceive, react, and adapt to the vehicle's behavior. It's essential for systems like ADAS, Advanced Driver Assistance Systems, lane keeping assist, adaptive cruise control, and automatic emergency braking, electric power steering and braking systems, tuning feedback and control feel, autonomous and semi-autonomous vehicles, studying driver and or behavior, vehicle dynamics control, ensuring smooth transitions during cornering, acceleration, and braking. In short, DIL combines engineering accuracy with the human experience. 10 things verified in driver in the loop: human machine interface usability, evaluating how drivers interact with the displays, buttons, alerts, and menus, driver reaction and response time, measuring how quickly a driver reacts to hazards, warnings, or control changes, ADAS feedback quality, tuning lane keeping assist, adaptive cruise, and braking alerts for comfort and confidence. Vehicle dynamics perception, verifying how real drivers feel steering, braking, and throttle behavior under different conditions. Comfort and ergonomics testing, analyzing motion cues, vibration levels, and seat dynamics during simulation. Driver workload and stress analysis, using biometric data, heart rate, eye tracking to measure cognitive load. Safety system effectiveness, validating how quickly driver take control during emergency situations. Driver behavior modeling, collecting data to refine virtual driver models for automated system calibration. Training and validation of autonomous systems, observing how drivers respond to AI driven maneuvers. System tuning for realism. Adjusting steering assist curves, braking feel, and throttle response to match real world comfort. Let's imagine you are testing a lane keep assist feature. In Hill, you validated that the ECU keeps the car within the lane using camera and steering torque inputs. But in DiL, you put a real driver in a simulator with a curved highway scene and realistic road textures. Now, as the car drifts slightly from the center, the lane keep assist system nudges the steering wheel. How does the driver feel that correction? Is it smooth or abrupt? Does it build confidence or cause surprise? Does the driver trust the system or switch it off? These are insights only DiL testing can reveal. Engineers record steering torque feedback, driver control inputs, vehicle trajectory, and even facial expressions to understand driver comfort and system expectance. If the steering connection feels too aggressive, engineers fine-tune control parameters and retest, all without ever leaving the simulator. Let's talk about the technology behind the DiL simulators. Modern DiL simulators are incredible pieces of engineering. They include motion platforms with 6 degrees of freedom, simulating acceleration, braking, and cornering forces. High resolution panoramic screens or VR headsets for realistic visuals. Force feedback steering wheels and pedals that replicate road feel and vibration. Eye tracking and biometric sensors to analyze driver attention. Integrated IL systems so that real ECUs can drive the virtual vehicle. In fact, many OEMs like BMW, Ford, Volvo, and Tesla use DiL simulators to test driver comfort, ADAS tuning, and even autonomous control logic long before building prototypes. Data from DiL testing. DiL testing isn't just about human feedback, it's also about data. Engineers record hundreds of variables: vehicle position, yaw rate and acceleration, steering torque and driver input angle, eye gaze direction and reaction time, heart rate or galvanic skin response to measure stress. This data helps correlate vehicle behavior with driver response, forming the foundation for future driver assistance algorithms. For example, by analyzing where drivers look before lane changes, engineers can design better warning systems that predict driver intent rather than just react. Safety and validation. DiL testing also plays a critical role in functional safety and human factors validation. When developing ISO 26262 compliant ADAS or autonomous system, you must prove not only that the system works but also that it interacts safely with human behavior. Through DiL testing, you can analyze when the driver takes over control, how long it takes for them to stabilize the car, whether they understood system warnings correctly. Such studies ensure that automation is not only safe but also intuitive and predictable for real users. DiL offers tremendous benefits. You can simulate dangerous scenarios, icy roads, tire blowouts, or pedestrian crossings safely in a lab. You can test hundreds of drivers and gather diverse behavioral data without using a single real vehicle. It drastically reduces prototype cost and accelerates development for ADAS and autonomous systems. In essence, DiL merges engineering validation with the human experience, ensuring that the vehicle's intelligence and the driver instincts work together harmoniously. So, to recap, MIL verifies your algorithms in a virtual model, SIL tests your real code in a simulated environment, PIL validates your code on the target processor, HIL confirms your ECU works with the real hardware connections, DIL ensures your driver trusts and understands your vehicle's behavior. It's the stage where engineering meets psychology, where zeros and ones translates into confidence and comfort behind the wheel. Next up, we move to the final stage, vehicle in the loop, where all components, including the real car, enters the picture for ultimate validation.